So far we have discussed the generation of code, but one thing that we may have noticed is that there's a lot of work that is done while creating temporaries and then erasing them. So to create temporaries, we would push into the stack and we would execute at least a couple of instructions, which one would be to decrement the stack pointer, and to pop we would increment the stack pointer, and we would do it once for every temporary that is created. So one observation here is that stack allocation and deallocation costs are independent of the size of the allocation or deallocation. So irrespective of whether I allocate one temporary or whether I allocate 10 temporaries, the cost of doing that is same, because it's just one instruction, which is the add instruction on $SP. So that's an interesting observation. And so using that, maybe I can kind of do an analysis over the program and to see what is the maximum number of temporaries that I would need. And depending on that, I basically a priori allocate that many number of temporaries in my potentially in my stack. And then while I am generating the code, I know which temporary to use, and so that would work nicely. The biggest problem here is, how do I know how many temporaries I need a priori, right? Okay, so here's one strategy, and this is just one of the strategies, that for every function body, estimate the maximum number of temporaries that may be required to evaluate it, right? So there are two things here. One is, I am basically doing this for every function body, all right? So I'm doing it individually for every function body. Instead of trying to estimate the number of temporaries that may be required for the entire program, I do it for every individual function body. And then that's meaningful because we don't know how many functions will be called, how many times a function will be called. For example, if it's a recursive function, at compile time, at code generation time, it's very difficult to figure out how many instances of this functions or activations of this function are going to be called. And so at a global level, it is not possible to estimate the number of temporaries that the program will need. But at an individual activation level, it is possible to do that. It may be possible to do that. In our language that we have been looking at, I'll show that it is actually possible to do that. And also, because we are going to do this at the granularity of a function body, the best place to store these temporaries, which are pre-allocated, would be in the activation record of that activation. Also, these allocation can be done at function entry. So, and the deallocation can be done at function exit. All right. So this is just like, for example, an activation record. So some part of the activation record is allocated on function entry, and that part is also deallocated, including the part that is allocated by the caller at function exit. And so if we just put the temporaries as part of the activation record, this deallocation and allocation can piggyback on the allocation and deallocation of the activation record. All right, so this is a function definition, def fib x equals, so this is the canonical example that we've been using for Fibonacci series. So fib x equals, if x equals 1 then 0, else if x equals 2 then 1, else fib x minus 1 plus fib x minus 2. Alright, so we want to generate the code for this, and the question is, how many temporaries do I need to evaluate the body of this function? So I'm not interested in the definition, but what is the number of temporaries that is required in the body of the function. So notice that there is an assignment, and recall that for the assignment, there is an equality comparison, and which is a part of the if then else construct. And for the equality comparison, I first evaluate the LHS of the equality comparison and then save it as a temporary before evaluating the RHS of the equality comparison. So I will need one temporary for evaluating the equality comparison x equals 1. Right? Because while I am evaluating 1, I want to save the value of x, because 1 is going to be evaluated in A0, and so I need to save x on the stack. Similarly, the same logic applies for the second comparison. So the body of else of the first if now has another equality comparison, x equals 2, and so I need a temporary for x equals 2. Then we have these two function calls, fib x minus 1 plus fib x minus 2. And for these function calls, we will have to push the arguments on the stack. and also the frame pointer and stuff like that. Now some of these can be thought of as temporary space, and it's up to us whether we want to kind of pre-allocate space for this or not. I'm going to discuss this in more detail later, but let's say that we need at least one temporary each for the 2 recursive function calls. Moreover, we need to have one temporary for the plus sign here, right? So because of the plus sign, I need to, while I'm computing fib x minus 2, I need to save the returned value of fib x minus 1. And for that, I need at least one temporary for the sum of the 2 return values of the 2 recursive calls. And finally, I need one temporary each for x minus 1 and x minus 2. So if I want to compute x minus 1, the way I'm going to do that is I'm going to first compute x, then save it, and then compute 1. And so for that save, I need one temporary. It seems like we need a lot of temporaries, right? Because we need temporaries for computing each expression. But notice that, when I while I'm computing x minus 1, for example, I don't need to keep the temporary for this x equals 1, right? So, these temporaries can be reused. In fact, I'm going to show you guys in this module that the total number of temporaries that I need for this entire function is only 2. Okay, and so how do we arrive at this, and is there an automatic algorithm that can identify what is the minimum number of temporaries that I need to be able to execute this function without having to create temporaries on the fly? I just create these 2 temporaries, let's say for this example, at function entry, and then the code is going to use those 2 temporaries during the execution, and then when it needs to return, it just deallocates those 2 temporaries. Notice that these 2 temporaries are for one activation of the function. Alright, so to be able to compute the number of temporaries, I'm going to define this function called nt that's defined on an expression. So nte would return the number of temporaries required to evaluate e. And just like everything else, we are going to define nt inductively. So we are going to define nt for every different operator that may appear. And for a given expression, the way we are going to compute nt is we're going to do a top-down traversal of the expression tree to compute nt using our computation rules. So here's the first rule. Nt of e1 plus e2. So this is for the plus operator. I need at least... So to compute e1 plus e2, how many temporaries do I need? Well, the answer is whatever is the number of temporaries that I need to compute e1, that's at least I need that many temporaries to compute the temporary to compute e1 plus e2. So I need at least nt e1 temporaries to compute e1 plus e2. I also need at least nt e2 plus 1 temporaries. Why do I say plus 1 for e2? Because while I'm computing E2, I also need to hold on to E1's value. So I need one extra temporary while I'm computing E2. So whatever is the number of temporaries that E2 needs, I'm going to need that much. Plus 1, because while I'm computing E2, I need to hold on to E1's value. And for that, I need one extra temporary. And so we get this, this rule that NT of E1 plus E2 equals maximum of NT E1 comma NT E2 plus 1. All right. Why maximum? Because while I'm computing E2, I don't need to hold on to the temporaries that were computed within the evaluation of E1. Similarly, why NT? So that's the reason for max, because whatever are the temporaries that have been used for E1, I'm going to be able to reuse them during the computation of E2, except for one extra space that I need to hold on to the return value of E1. So that's the reason for max. All right, and so we're going to see the similar pattern everywhere. Once again, this is recursive definition of NT, and this is supposed to be pattern match. So this is actually a definition, a rule to compute the number of temporaries required for the plus operator appearing anywhere in the expression tree. Now, similarly, generalizing to other operators, if there is a minus, then I say NT E1 minus E2 equals max NT E1 comma NT E2 plus 1. Exactly similar to plus. Now, here's another rule for if then else. So in our language we have if E1 equals E2, then E3, else E4. So the rule for this is, recall that I can compute E1, and so whatever is the number of temporaries I need for E1, that's minimum I need. Then I need to compute E2 while holding on to the value of E1. So I need whatever is the number of temporaries for E2 plus 1. And then after I've done this computation, then I can release these temporaries that I had created for E1 and E2 and for the equality computation. And then I just jump to the computation of E3 or E4, depending on whether the condition was true or false. And so while I am computing E3 or E4, I don't need to hang on to any temporaries due to the equality comparison. And so the rule is NT of this whole if then else expression is max of NT E1, comma, NT E2 plus 1, comma, NT E3, comma, NT E4. Because the only place where we need to hold on to a temporary is while computing E2. For other things, we don't need to hold on to any temporary because of the if then else constraint. Alright, now let's look at a function called dispatch. So a function called dispatch looks like id e1 dot dot en, and the question is what's the number of temporaries that I need to pre-allocate for this function. Now this is a little bit of a subtle question, because you may imagine that while I'm computing the function called dispatch, I need to save the values, computed values of each of the arguments. So I need to save the value of E1, E2, En, and so on. I also need to save the value of the old frame pointer. And so it may be tempting to think of them as temporaries, and so we can pre-allocate space for them in our activation record. But there's a problem with this. The problem is a function called dispatch is special in the sense that there is a contract between caller and callee about where to expect the arguments, the actual arguments. So the callee should know where to expect the actual arguments, and that's where the caller will fill in the actual arguments. And so it will be pretty difficult to kind of pre-allocate space for that, because while we are pre-allocating, it's very difficult to kind of stick to those calling convention rules, because in this case we are just allocating some space in the activation record irrespective of where it is with respect to the other temporaries in the program. And so one approach to doing this, and that's the approach we're going to take, is that all the stuff that's allocated for the function called dispatch, including the frame pointer, is allocated dynamically. So for that, we are not going to pre-allocate at function entry. And so the only temporaries here are actually none. So the frame pointer is not considered a temporary in this scheme that we want to follow. The arguments are not considered temporary, or they're not considered pre-allocated temporaries. Let's put it like that, because they can be, we want them to be allocated as and when they are required. Alright, and so NT of ID E1 E2 dot dot En is max of just NT E1 dot 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 NT En. So because we expect that all the other temporaries, all the other space on the stack will be dynamically allocated. There is nothing really that needs to be pre-allocated for a function called dispatch, and so we're going to just assume that the function called dispatch can be computed without any temporaries of itself. It just needs to have the number of temporaries that's required to evaluate each of its arguments. Alright, so this max of NT1 dot dot NTEN. Finally, the base cases. So for NTInt, which is an integer constant, we don't need any temporary, so it's just 0. And similarly for NTID, we don't need any constant, it's just a load word instruction, so we just use a 0 there as well. Alright, so with that, we are ready to kind of run this procedure NT that we have just defined on the Fibonacci program that we use as a canonical example. And so whenever we see a body of the function, so whenever we see a function declaration, it would be associated with the body, and that's what we basically are going to compute. That's the top level program, or that's the top level syntax on which we are going to call the NT. So we're going to call NT on the body. So what the body here represents the entire body of this function. And what is it going to be? So we're going to use our implementation rule. The first rule that we're going to use is the if then else rule. So in the if then else rule, we're going to say that it is the max of NT E1, which is X, NT E2 plus 1, which is 1 plus NT1. So NTX 1 plus NT1, and then E3, which is NT0, and E4, which is this entire remaining expression on the else side. So NT of if X equals 2, then 1 else fib X minus 1 plus fib X minus 2. I haven't written the whole thing here, but that it's the remaining body of the function body. Okay, so this is what it evaluates to. Now what is ntx? That's just 0 because it's an identifier. We just saw that rule. What is nt1? That's also 0. So this becomes max of 0 comma 1. What is nt0 again? Again 0. So max of 0, 1, 0 is just 1. And then we want to break down this further. So we get max of 1 and then we break this down. So this is yet another if then else. So we use the same rule. So E1 is x, E2 is 2. So ntx 1 plus nt2. E3 is 1, so nt1, and then nt of whatever is the remaining body, which is nt of fib x minus 1 plus fib x minus 2, which is the remaining body, E4 of the if then else. Now once again, ntx is 0, nt2 is 0, and nt1 is 0. So this becomes max of 1 comma 0 comma 1 comma 0, which is again 1. And now we're going to break this down further. Now this becomes max of 1 comma, because of the plus, we are going to use the rule for the plus, and so we say nt of fib x minus 1, this becomes our E1, and 1 plus nt of fib x minus 2. So this becomes our E2, and 1 comes because while we are computing E2, we need to hold on to the computed value of E1. Alright, so we are almost there. Finally, this is a function called dispatch, and for a function called dispatch, we don't really create any extra temporaries, we just create the number of temporaries that are required for the argument. And so how many temporaries are required for the argument? The argument here is x minus 1, so the number of temporaries that's required is the number of temporaries for x, which is just 0, and number of temporaries that's 1, which is also 0, but I need to hold on to x while computing 1, so that's 1, so 1 plus 0, and so the number of temporaries that are required for nt fib x minus 1 is just 1, and nt fib x minus 2 is 1, and so this becomes 1, so this becomes max of 1 comma 1 comma 1 plus 1, which is 2. Alright, and so with that I know that I can do this with 2 temporaries. So this is just a computation of what is the minimum number of temporaries I need with my scheme of pre-allocating temporaries for all arithmetic and if then else operators, but not pre-allocating temporaries for function called dispatch. Alright, so this is the AR layout this was the original AR layout that we had said. This is the activation record. This is old FP, the arguments laid out in reverse order, and the return address, and this is where the frame pointer register would point during the activation. Now in the new layout with temporary pre-allocation, what I'm going to do is I'm going to allocate that many number of temporaries just below the original AR shown in this purple. So let's say temporary 1, temporary 2, and so on. Once again, I'm laying them out in the reverse order. So for a function definition, fx1 dot dot xn equals e, the size of the AR has now increased. Actually, why has it increased? Well, it has increased because now we are going to pre-allocate the temporaries as well. Earlier we were dynamically allocating and deallocating on the fly. Now we are pre-allocating at function entry, and so at function entry itself I had to allocate more. Overall, this is going to be an optimization because in any case I would have allocated that stuff, but I'm saving some instructions to actually keep moving the stack pointer up and down. Now the stack pointer is going to move less because I've already pre-allocated. You may think that this is a problem because you are wasting more space because you're taking extra space for a longer amount of time, and that's true. So in fact, this is an optimization that's trading off space for time. We are using more space over a larger amount of time to reduce the number of instructions, right? And this is this will usually be an optimization because the amount of space that we are demanding, the extra space that we're demanding, is very, very small. It's only a few temporaries, few words. On the other hand, the amount of time that we'll save is also a few instructions, but those instructions are going, they're going to be consequential because the time is basically just proportional to the number of instructions, let's assume. All right. Okay, so for a function definition, fx1.xn, the AR has 2 plus n, where n is the number of arguments, plus nte. So what is the number of temporaries calculated for e by our previous algorithm? That's the total size of the AR. This is words. So in bytes, this will be multiplied by 4, right? So I'm assuming that each word is 4 bytes. Okay, so now let's, we just discussed how do you determine what is the number of temporaries you need for a function body. We also discussed what's the new activation record structure that is going to need to be allocated so that you can pre-allocate that many temporaries. But then how do you now generate code to use these pre-allocated temporaries? Earlier our code strategy was just allocating and deallocating temporaries on the fly, but now I want to use these temporaries as well. And so to do this, I'm going to add a new argument to our cgen function, the code generator function, and the new argument is going to be nt. Nt is going to be a constant at code generation time. So this is going to be known constant at code generation time. And what it will represent is that nt is the position of the next available temporary. All right. So I'm going to assume that in this picture, the temporaries are kind of laid out as a stack, and so the first available temporary is going to be T1. The next available so if T1 is used, the next available will be T2. And unlike our usual convention, I'm going to assume that these temporaries are growing. The stack is growing bottom to top rather than top to bottom. Okay, so it doesn't matter. You could have used any other convention as well. You could have used the stack to grow top to bottom as well. It doesn't really matter. Okay, so the temporary area will be used as a small fixed size stack, right? Because an NT will keep increasing or decreasing to indicate the current top of or the next top of the stack. So because it's a position of the next available temporary. So any pushing should be happening at NT. Initially NT would be pointing to the location where T1 is supposed to be put. All right. And we can offset this through $fp to identify variables or arguments and temporaries. All right. So just like we were offsetting through $fp to identify variables, what were we doing? We were saying fp plus n into 4 plus 4. That's what we were doing. Or fp plus n into 4 if n is starting from 1. Now we're going to change the offset for variables because we also say now we'll have to say fp plus nt E, which we know at compile time, what is the NT that has been calculated for the body, plus 4 plus 4 into n, right? So we're going to have to change the offset for the variables accordingly. Also now we can now address the temporaries. We can, if we want to say T1, then that's just fp plus 0. If I want to say T2, then that's just fp plus 4. So if I just go back to my figure, T1 is at fp plus 0, T2 is at fp plus 4, and so on. Alright, so with that background, let's look at our code generation implementation. So originally, before we used temporary pre-allocation, cgen function for E1 plus E2 would look like the following. We would first do cgen E1, then we would push the value of E1 on the stack. And so this is exactly the temporary allocation, right? Then we would compute E2, and then finally we would load the value from the stack, pop the stack, right? So these are the extra instructions, popping and pushing, the ones that I'm pointing out with arrows. I'm just wasting time popping and pushing small stuff. Why not I just do this once in the beginning and then keep reusing them? So how do I do that? Well, here is our new implementation with stack pre-allocation. As I said, the cgen function now takes an extra argument nt, and so cgen E1 plus E2 nt. And recall that nt is the compile time, code generation time constant. So I know what nt is. And so I say cgen E1 nt. So compute E1 such that the next temporary can be pushed at whatever is the value of nt. Right? Recall that nt is basically where can the next temporary be used. Where should I use? Which space should I use for putting the next temporary? So I can compute E1 with the same value of nt. And then I can store the computed value at $sp. Okay, so what does that mean? Now, whatever is the space that was used by E1, it doesn't matter. I don't need those values anymore. But now I can save the computed value to nt because that's where I want to save the computed value of E1 before I start computing the value of E2. And so when I call cgen of E2, I need to be careful because I don't want the computation of E2 to clobber the value that I've saved for E1, and so I basically change my argument to nt plus 4, right? So which basically means now if computation of E2 requires some temporary space, then it should start from nt plus 4 because the nt is now taken by the value of E1. Now, the other way to, so let me finish this, and then finally I'm going to say just the same thing, load word $T1, but instead of $4 SP, I'm going to say nt $fp, all right? So this is actually this is a mistake. It should have been an fp here in both places. We are actually doing this relative to the frame pointer and not the stack pointer. All right. So so is a load word $T1 nt $fp, And then I finally do the addition operation, which is add $A0, $T1, $A0. And I don't need to do any popping, right? Because anything that was calling it knows that now, whatever is the temporary space that was used for E1 plus E2, I don't need to bother about it, and it can do it can kind of start reusing that as well. So in other words, what is the invariant for CGen? Just like earlier, the invariant was that I will not modify the stack. The new invariant for CGen is I will not modify the stack, that's true, and compute the value in A0, but also that I'm not going to touch the temporaries below NT. Right? So I'm not going to touch any temporaries below NT, I'm only going to use the temporaries above NT, and that's the invariant that we can assume for CGen, and using that invariant we can show that this implementation of E1 plus E2 is correct. Finally, how do I initialize NT? Recall that I said that NT is a compile time constant. So how do I know what is the compile time constant that I use from the initial value? Well, that's easy. Anytime I see a function definition, recall that we are doing this temporary pre-allocation at function granularity. So for every function body, we are doing separate things. For every function activation, in that sense, we are going to have separate pre-allocation. And so earlier we were saying CGen def f, so we would say CGen and then the expression, and the expression could have been a function definition. Now we're going to say anytime you basically do a CGen for a function definition, you start with offset 0 for the for that function while computing the body of that function 0. So that's so the value of NT will be initialized to 0 at every function definition in the abstract syntax tree. The reason it will work when the value of 0 would work is because I know that I've already computed what's the maximum number of temporaries I need, and I've allocated that much amount of space in the activation record. So I know that if I start from 0 here, then the computation would proceed safely and will never overflow the space, temporary space. For example, if I had started from some other number, for example, if I started from 4, then I wouldn't have been safe, right? Yeah, so that's the idea. Also, starting from negative number doesn't make sense because that would underflow the stack, and so that doesn't make sense as well.